Hi folks. So we're going to do one more problem. It's number 52 in the back of our chapter. It says, I've altered this a little bit, just a by the by. I'm going to read it in a second, but I did alter this. I gave it actual numbers. The original problem simply asked us to find expressions, but I wanted to put some actual numbers to this. So our problem says, use work and energy to find the speed of the 4 kilogram block, just before it hits the floor if we have two scenarios. A, the coefficient of kinetic friction for the block on the table is 0.2, and then B, if the table is frictionless. So this is our scenario here. We have a pulley system. We have a 4 kilogram block suspended 5 meters above the floor. And then I have a 3 kilogram block sliding across the table. And there is a pulley and a rope or string that connects both of them. So let's actually start figuring out this first one. The coefficient of kinetic friction for the block on the table is 0.2. We'll just quick write that down. Okay, 0.2. This is for part A. So what we're saying here is that I have two elements of my system. They're both going to be moving and both going to have changing energy quantities, but there's also work being done by the environment. So this is a non-isolated system. We're saying that the total change in mechanical energy of our system is equal to the external work being done. So if we split this up a little bit more, we can say delta K, or kinetic energy change, plus delta UG, which is our gravitational potential energy, and of course delta UE. Now I will say that there are no obvious springs in this problem, so we can just go ahead and say that there's no change. There's really no potential energy that's stored elastically. All of this is equal to the external work done in our system, or the work done by friction, right? So this is all well and good, but we've gotten into a bit of a habit of talking about the initial stuff, then the external works being done, and then all the final energies. So the initial energies are a little bit different than what we did before. We have two systems, right? We have not two systems, one system, but two blocks, two bodies. So I'm going to call this 1 and this 2, right? We're going to do it algebraically, but then we'll plug in some numbers to actually get an answer. If I think about what I have initially, I have an initial kinetic energy for block 1 and possibly an initial kinetic energy for block 2. Likewise, I'm going to have a potential energy for block 1 initially. It's a lot of subscripts. And then gravitational potential energy for block 2. We already said that there's no elastic potential energy, and this is where we normally plug in our external work. Then we say that it's equal to the final kinetic energy of block 2, or block 1, sorry, plus the final kinetic energy of block 2, and then of course gravitational potential energy for block 1, final UG2F. So that's a big equation. That's a big, very long expression here. Let's start thinking about what maybe goes to 0 or what can cancel. First things first, we should probably set where is UG equal to 0. We should set that that precedent, right? I would say it makes sense to say that right at the bottom here, right at the bottom, UG equals 0. I think that makes a lot of sense. And so I have some initial potential energy, some initial gravitational potential energy for block 2, but I won't have any final potential energy for block 2 because we're considering it just before it hits the floor. and so we are not at any appreciable height above the floor. If I think about the gravitational potential energy of block 1 here, really I never change heights. So UG1I and UG1F are the same, and they'll cancel then. I can subtract both sides by it. Lastly, I need to consider the initial and final kinetic energies of these blocks. The initial kinetic energy of this system is 0, right? We're considering it just before we let go of the system and letting it kind of go into motion. So both of these terms are 0. And then when we consider the final kinetic energies, they have to be moving at the same velocity. They're part of the same system. They must have the same VF. That's important. That's really important for us to remember. So, what remains? Well, we have UG2I, that's M2GH. I have the work done by friction. Work done by friction, well, that is going to be our normal force times mu k. Our normal force here is going to be equal to mg. So I'm going to have m1g times mu k. Now, how far does it move during this system, right? Well, if we consider the rope being taut, block 2, the 4 kilogram block, moves down 5 meters. The only way for it to move down 5 meters is for block 1, the 3 kilogram block, to actually move to the right 5 meters and give 5 meters of rope. So I actually have the same displacement in both of these blocks. I have h in both scenarios. And then finally, there's a cosine of 180 degrees because our friction force always opposes the displacement. This is just going to be a -1. If we wanted to, we could actually just say, let's get rid of the cosine of 180 and just throw a negative sign in here. That's perfectly fine. That's perfectly fine. That's what we have initially. This is our initial energy in the system. This is the work done by the environment. And then I'm saying that the whole thing needs to then be equal to our kinetic energies at the end, where I have 1/2 m1 plus m2 times Vf squared. And I said that they need to have the same Vf for this rope not to break, for the system to be complete. And so this is my final energy in the system. All right, so at this point we can start to solve for Vf. I can say Vf is going to be everything on the left-hand side. I've kind of flipped the two sides. I'm saying it's, let's pull a G out maybe. G times M2H minus M1 mu K H. Yes, I could have pulled an H out too. This is silly. Let's just write it the way we had it. M2GH minus M1GH mu K, I've rearranged that slightly, over 1/2. Well, let's just multiply this by 2 on top and then divide by the sum of my masses on the bottom. Then I take a square root of the whole thing because V is squared, and I'm able to get some numbers. Right? So I'm going to plug in some numbers. I'm going to plug in 4 kilograms for mass 2. Plug in 9.8 meters per second squared for G. I'm going to plug in 5 meters for H. Mu K is going to be 0.2. And then M1 is going to be 3 kilograms. When I evaluate this, I get a velocity of 6.9 meters per second. So that's the velocity of the 4 kilogram block right before it hits the floor. It's also the velocity of the 3 kilogram block right before the 4 kilogram block hits the floor. They're both moving at the same speed, but it's easier to say when 4 kilogram block hits the floor. It's easier to put in terms of that. So now for part B, what if the table was frictionless? Well, everything in our energy analysis is true still, except this guy. Let me actually do it in red here. This guy, right, my external work, is now 0. And so that means that this whole term goes to 0, this whole term goes to 0, and I'm left with a VF equals a square root of 2m2gh over m1 plus m2. Much simpler expression, and when I evaluate that in my calculator, I get a value of 7.5 meters per second. Now let's consider this for just a second, and then we'll finish up. Does this make sense? Well, if the table is frictionless, that means that I have less resistance up on block 1, right? It also means that there's more energy in my system to convert, into kinetic energy. This external work being done, this work done by friction, is taking energy out of my system so that I cannot convert all of it into kinetic energy from potential energy. So this is now a more efficient system, and it makes sense that I'm moving faster. I've converted all of my potential energy in block 2 into kinetic energy for the entire system. Notice that both of these blocks are moving, so both of them have kinetic energy. We can't just focus on block 2. We have to consider block 1 moving as well. Otherwise, we won't come up with the correct expression here. So that's actually part B. That was it. Part A was all the heavy lifting. Part B is just saying that the external work is equal to 0. So that was number 452. If you have any questions, please come swing into an office hour or email me. That's perfectly fine as well. And I'll see you later.